Okay, I got some additional visual aids here that I'm going to start sending around. David, if you could do the honor of being the launcher here. This should probably go in about 1, 2. Yes, exactly. These are real tiny chips. So I went to the dollar store and I got a Fresnel lens, so you can see the fine details of everything we're going to try to show you here. Whoops.
I didn't bring my microscope tonight. So.
Well, my microscope got a workout on this project. Okay. All right, I'm David Shuman. I've met some of you before. I've been coming to this group for about 3 years. I gave one talk a couple of years ago about making printed circuit boards. Thought I'd start off with a little about myself. My motto is I make new parts for old things, and that includes things like this old video arcade game here. I also work on pinball machines. I love synthesizers, and recently I've started restoring old Hondas. So that's a little about myself. Another thing I noticed in putting this slide together is when my right hand is taking a selfie, my left hand automatically goes like this. You got it? Okay. What are we talking about tonight? Name of this talk is the rebirth of the Pokey. What's a Pokey? It's a chip. It's this chip. Atari made them back in the 80s for about 8 years and put them into their arcade games and their Atari 400 and 800 computers. They put them in the 5200 game console, and some Atari 7800 cartridges have Pokeys in them. In this particular game, the things we're talking about are these two chips right here. Now, these are not original Pokeys. These are the things I made. And also, you know, what are we looking at here? This is a computer. This is a self-contained microcomputer, circa 1980. This is a 6502 CPU, which makes this game sort of the cousin of home computers that use the 6502, like the Atari home computers and also the Apple II. That was a 6809. Oh, yeah, I can't leave out the Commodore. One thing I'm going to keep mentioning over and over again about the Pokey is that it is an example of an ASIC, which stands for Application-Specific Integrated Circuit. And by application, I don't mean like a software application. I mean that the circuit is specific to whatever it is you want to do with it. It is not a general purpose chip like a 74 series logic chip that does the same thing no matter what you put it into. An ASIC is meant for one project or one application and one thing only. The CPU that goes into your laptop is an ASIC. The graphics coprocessor is an ASIC. The Ethernet interface in your laptop is an ASIC. This is the PokeyONE. This is the thing that I made. Now, this is not, a conceptual drawing. This thing is, as of about 10 days ago, finished and on sale, and you can buy one right now. They make great Christmas ornaments. This thing has taken about 18 months of work to get to the finished stage. It has been my obsession. And I was not sure it was ever going to get done. But you're going to hear the story of how it did. While we're all looking at the PokeyONE, I should mention it is not an ASIC. It is not an application-specific integrated circuit. It's not really an integrated circuit at all. It's a daughter board. And you see it's got legs on it. And it plugs into the chip socket on the motherboard, just like the original chip did. This big sucker right here is the heart of the whole thing, and that is called an FPGA, a Field Programmable Gate Array. What is that? We're going to talk a little bit about that in a moment. First, let's talk about why a Pokey is a Pokey. The name comes from what it's sort of originally intended to do, to handle the potentiometers and the keys in an Atari home computer. And you can see, the green things correspond to the pins on the Pokey that the pot's attached to. Yellow ones are what the keys attached to. Potentiometers and keys, Pokey. The geniuses who designed this thing, they had a real good idea. They said, hey, we need timers to do all this keyboard and paddle scanning. But as long as we've got timers built into these things, why don't we use the same timers to make sound? And that's exactly what they did. The Pokey has timers in it, 4 channels of them, and each of them counts down from some value you load into it, something between 0 and hex FF. When it reaches 0, it takes the line that represents the audio output, and if it's a 1, it makes it a 0, and if it's a 0, it makes it a 1. It toggles it. So by playing with the timers, you can get the chip to output a wave that looks like this. And if you attach that to an amplifier and then to a speaker, you get sound, as I'm sure all of you heard coming from that beast over there a minute ago. What did I want to say about Pokeys? They're expensive. They didn't used to be expensive, but they certainly are now. There's a few reasons for that. When Atari made these for 8 or 9 years, they made over 1 million of them. And, enough that for a long time you could get as many as you wanted for $1 each. You could buy them by the case. People who had them couldn't get rid of them fast enough. Well, as the 90s wore on and the 2000s and we got into the current decade, more and more people started collecting things that Pokeys go into, like these arcade machines and like Atari home computers, and the demand actually went up for this ancient chip. So as your supply is getting smaller, your demand is getting bigger, and to compound things, very recently, the chips have started to fail. Now you say, well, how can a digital chip fail? I wish I could answer that. I wish I knew what went wrong with these things when they go bad. But I have repaired enough arcade machines in the last 25 years to know that, 10 years ago you rarely saw a bad Pokey, and now you see them all the time. Another reason for this price curve going way up.
They last 30 years, they're doing great.
Yeah, well, most of them did last 30, but a lot of them are not going to last 40.
Sounds like, PBS special when good Pokeys go bad.
Well, that could have been this talk.
Next time.
Yeah, sure. There is one good part to this price curve, which is at some point it becomes possible to recreate a Pokey and make it economically feasible. I'm not going to pretend that I invented the FPGA version of the Pokey. Other people have written Pokey cores that they've released various times over the last 15 years. But if something, is designed for a single game and requires a $50 FPGA dev board to run and hangs out of your machine on a ribbon cable, nobody's going to want to buy that. So my mission became to recreate the Pokey in a way that you could use my product the way you would use the original thing. Something that was about the same size and shape and same function as the original chip. To do that, of course, we got to know how a Pokey works. You can't tell by looking at it. It's just a plain old black plastic package with 40 little legs sticking out of it. One thing we could do if we were real masochists is we could take some nitric acid and burn the package away and expose the silicon die itself and chuck it under a very high-powered microscope and look at how the transistors are laid out on the die. You can do this. If you have a lot of money, you can reverse engineer somebody else's ASIC by doing exactly that. And if you were to do that with the Pokey, you'd see this. This is the Pokey.
Wow.
Since this is so beloved to hobbyists, people have generated a lot of interesting documentation about what goes into this chip and how it works. And a lot of that was indispensable to me in trying to recreate it. But if the original chip, this is what's inside it. This is 6 millimeters by 6 millimeters, so about the size of the nail on your pinky finger. For comparison, here's a human hair. If we zoom in a little more, the hair gets fatter and you start to see a little more structure. There are people who make a living decoding these things. They can actually look at this and tell you, oh, that's an N-doped area, that's a P-doped area. This whole thing makes a transistor, and these 8 transistors together make an OR gate, and these 3 OR gates together make a flip-flop, and this is all part of some greater logic structure. These people must be wizards, because I can't imagine doing something like that. Let's zoom in one more time just for fun. I said, let's zoom in one more time just for fun. Remember when I said what was going to go wrong? Oh, they've shut me down. Laser still works. We could just look at this slide the rest of the time. There we go. Okay, now we've got a big fat human hair. These traces inside the Pokey, these are 6 microns wide. So by modern standards, they're enormous. 10 of these little yellow lines would fit inside one of these green traces. 1/10 of 6 microns is 600 nanometers. That is the scale that Intel was using for its CPUs in 1991. Intel's current scale is 60 times smaller than that. It's 10 nanometers. So, a 10 nanometer line wouldn't even be visible at this scale. It would just be atomic size almost. That just blows my mind. They may be. They keep teasing things that are less than 10. And I think they've teased things all the way down to 4. But they're having trouble. Not surprisingly, they're having trouble. I've read a lot lately about the lengths you have to go to generate light of a short enough wavelength to lithograph a circuit at that scale. And the answer is you need like extreme X-rays, which turn out to be not at all easy to generate. So it's all just black magic. Okay, we're back in business with the clicker. Maybe you won't be going back to Amazon after all. No thanks, we don't want to look at the die and trace out all the transistors. If only we had a schematic diagram that would tell us how this circuit is put together at a higher level of abstraction. Oh, well, we have something like that. Somebody actually got the original schematics from the Pokey, from Atari, from years ago. I mean, I'm talking like 1979. And they're marked confidential, and the pages are actually yellow with age, and they're not entirely legible. But somebody actually took it upon themselves to recreate the schematics and draw them up with a nice CAD program and make them readable. The schematic for the Pokey is 5 pages, and this is about half of 1 page. That gives you some idea of the complexity that goes into that big old die. Yeah, 5 pages. So we're Nash Micro. What's the micro in Nash Micro? It's microprocessors, right? We all might have the idea, well, why don't we create an embedded software system based around a microprocessor? And to perform the things that the logic internal to the Pokey performs, we'll just write some code, and we'll compile it, and we'll pack it into our microprocessor. Bob's your uncle. Microprocessors have a lot going for them. They're small, they're cheap, they're easy to get in just about any flavor you want. They use almost no power. The documentation on how to use them is wonderful. Why not use a microprocessor? Well, somebody had exactly this idea back in 2014, and on the Atari Age Forum, they announced a product that they called, bear with me.
Nolan Bushnell's behind the scenes playing tricks on you.
Thanks, Nolan. Yeah, we're back in action just about 20 slides behind. Okay, in 2014, the Hokey was announced. And from this picture, you can just barely discern that this is an NXP LPC1313 microcontroller chip. It's a little ARM Cortex-3 chip. You can get them for about $3 a piece. And the internet's response was heart, smiley face emoji. People said, that's great. When can I get one? Well, the answer is never. The Hokey was never released. Why not? It is instructive to ask that question. It's never been explained any place I read why the Hokey never became a real thing, but here's my best guess. The Pokey chip does many things at once, all of them in parallel with each other. You have 4 channels of audio being generated. You have a mixer and a set of filters on each of those 4 channels. You have 3 so-called linear feedback shift registers, which are these funny little gate arrays that basically generate bit patterns. And when they're long enough, like 17 bits, the bit pattern approaches randomness. So you can use it to generate random numbers. And in fact, what the Pokey does with these things is it mixes pure tone square waves with the outputs of these shift registers, and it makes them noisy. And a 4-bit shift register mixed with the square wave will sound like an engine. It kind of goes rah, 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 because it repeats itself after only a dozen bits or so. Whereas a 17-bit LFSR sounds very much more random. So it sounds like white noise. It goes sss. This turns out to be very useful if you're building an arcade machine like Tempest or Missile Command or what have you. Of course, the Pokey's also got a digital analog converter in it, so that turns the digital signals into something you can pump through a speaker. Like I mentioned, it also scans the keyboard and the paddles if any are attached, and to get data into its registers and back out to the CPU, you've got an I/O unit, and you've also got serial input and output, which an Atari computer runs the modem or the printer or what else? Anything else a disk drive, you can plug into that port on the Atari 800. That's serial I/O. Microprocessors, as we all know, execute instructions sequentially. They can't do more than one thing at once. They do something, and then they do something else, and then they do the next thing. It can do this as fast as you can clock them. The Hokey microprocessor, I looked at the data sheet, it can run up to 72 megahertz. Which, for a $3 chip doesn't sound so bad. But the fact is, I bet the microprocessor in the Hokey cannot execute fast enough to do everything a Pokey does in the time that you have to do it. A Pokey runs at a little less than 2 megahertz. So, invert that, and that's how many nanoseconds or microseconds you have to do everything a Pokey does. And the fact is, you just can't run your microprocessor code fast enough to get it all done before that next clock pulse comes in. Here's a better idea. We can recreate an ASIC using an FPGA. An FPGA is also an embedded processor, but it's embedded hardware. It has no software. And you might think of it as functionally equivalent to an ASIC in that it creates an actual electronic circuit in which every part of it operates simultaneously, which makes it ideal for doing a lot of things in parallel with each other. In an ASIC, the circuit we're talking about is permanently fixed in silicon, like that die that we took such a close look at. That's the circuit. It's burned in there at the factory, and you can't change it. FPGA, on the other hand, as the designer, you get to configure the internal logic, which are arranged into so-called cells, to define the circuit. And then when inevitably it doesn't work, you get to redefine the circuit, and then you get to redefine it again. Here, basically the process is this. Here's you. Here's a blank FPGA, and through some kind of magic, you can turn a blank FPGA into just about any kind of ASIC equivalent you want, a CPU, a chip that does nothing but process bitcoins all day, Or if you have a particular kind of madness, you can try to turn it into an Atari Pokey chip. What's involved in the poof? What is the poof? How do you turn a blank FPGA into one of these incredibly valuable and useful ASIC equivalents? Well, you write code for it. This code for an FPGA is written in what we call an HDL, Hardware Description Language. There are two real common ones, VHDL and Verilog. There's also a new one called System Verilog, but it's basically Verilog with some more bells and whistles. Here's an important point. I'm talking about code, so when you think about code, you might think about writing a program. But an FPGA doesn't run a program. It's not a processor that takes one instruction after another and executes them. An FPGA is a circuit, and you don't really program a circuit. This is sort of a fine point, but it's really useful to keep in mind, especially when you start programming FPGAs, because everybody comes from a software background, and you figure, well, I'm going to write a program and tell this FPGA what to do. That's not really how it works. What you're doing is you're telling the FPGA how to configure its internal logic so that when you turn it on, it does whatever it does. That's the difference between a physical circuit and a general-purpose CPU running a program. FPGAs can be fantastically complicated. For practical purposes, you're limited only by the number of logic cells you have available to configure, and perhaps even more importantly, how much I/O you have. When you talk about FPGAs, you're often talking about being I/O limited, which means, hey, I've got plenty of room inside my chip, but I don't have enough pins to connect to get all the data in and out of it that I want.
Question. You can make memory inside your FPGA, right?
Yes, you absolutely can.
In theory, then, you could program that memory to make the FPGA processor do what you want.
Yes, you could put an FPGA inside an FPGA. I don't know, that might be kind of an interesting exercise, actually.
It's part of the whole thing. It's part of the chip. You can make part of it into, say, ROM.
Oh, yes, absolutely. And we're going to talk about doing exactly these things.
That's RAM over here. But it'd all be within the FPGA.
Quite so. FPGAs are often used to create what we call systems on a chip. That is, they will be an ASIC in which are contained a CPU core, a RAM core, a ROM core, a UART core, a receiver transmitter block, so you can talk to the outside world. And all these things can get coded up in a VHDL or Verilog module and put together inside your FPGA, and all these things sit side by side with each other and work at the same time. So it's the equivalent of taking a whole board full of discrete logic like this, and with an FPGA you can condense the whole thing down into one chip. In fact, I've done exactly that. I did a project where somebody took the entire logic board for Asteroids Deluxe and put the whole thing into one FPGA. That's kind of what got me started doing this. I thought that was so amazing I couldn't stop thinking about it. So, we're talking about complex FPGAs. Here's a complex FPGA. This is pretty much the big daddy right now. This is a Xilinx Vertex Ultra Scale Plus. And you can have one. One chip about 2 inches square that weighs about as much as a paperclip for a little less than $90,000. It has about 4 million logic cells in it, and it's got about 2,600 inputs and outputs. Now, many of those are dedicated to power, so you can't use them all. I think this actually has 1,200 IOs you can use. What a pity.
Is that radiation hardened too?
That costs extra. And if you want pinstripes, they're going to charge you for that too. Fortunately, I don't really have any need for something with this much horsepower because I'm not building a high-frequency trading system out of bare metal, and I'm not designing the next generation Intel CPU. For things like that, you might need a development board that has 4 or 6 or 8 of these things together. And sure enough, they will cost you $500,000. But if you need it, they're available. At the other end of the scale, we have something like this. This thing is about this big. 640 logic cells, which is actually kind of a lot for the things that you might want this thing to do. It's got 16 balls, and 10 of those you can use for input and output, and you can have as many as you like for $1.41 a piece. This is great if you're building a cell phone and you need a really tiny chip to get in there and replace what otherwise might be some discrete logic. So what's our idea? Our idea is to take a cheap, small FPGA, maybe not that cheap and that small, but certainly towards that end of the scale, and turn it into the equivalent of a POKEY. What are we going to need? We're going to need about 1,000 logic cells, so really only a few more than that were in that itty-bitty chip we just looked at. Counting up the lines in and out from the POKEY schematic, looks like we're going to need about 40 IOs, which is kind of a lot. And to make this thing economically feasible, because we don't just want to make it for ourselves, we'd rather make a lot of these. As they say, what's worth doing is worth doing for money, right? In fact, I'd prefer it's less than $3 because, of course, whatever you build is going to have to compete with all the original Pokeys that are still in the market, and if they only cost 30 or 40 bucks, you can only charge 30 or 40 bucks. Fortunately, you can now buy FPGAs that are that small and that inexpensive. So I say, let's do this. And that's why I added that emoji there. It looked suitably deranged to express how crazy you have to be to attempt this. So let's take a brief break and summarize what we've talked about. If you take away one thing, it's that there are these things called ASICs, application-specific chips, and our friend the Atari POKEY is one of them. I made the PokeyONE, which is an FPGA recreation of the original POKEY, an FPGA being essentially an ASIC that you can reprogram. And finally, FPGAs are great for things that microprocessors are not so great at, which is parallel execution. So let's get into my product, the PokeyONE, and see what that's all about. Here's where we're going to go. And this is not only about the PokeyONE specifically, but it's about designing generally, engineering generally, and specifically hardware engineering. The thoughts that I had to think and the decisions that I had to make over the last 18 months to get this thing from conception to actually being on sale. Asking questions about, is this project doable at all? And if it is, well, we've got to write a specification, got to talk about what it's required to do as far as performance, and what are our limitations in terms of physical constraints like size, and what are our cost constraints? What's possible for us to do realistically? Then I'll talk about how we select parts based on the constraints and requirements that we've defined. I'm going to talk a bit about programming the FPGA, and you'll note that I properly put programming in quotes because, of course, we're not writing a program, we're writing a description of a circuit. I'll give an example of some VHDL and talk you through that, hopefully whet your appetite for writing some on your own. And then I'll show you a block diagram of how the PokeyONE is arranged and how my VHDL modules nest within each other in this hierarchy. Of course, this isn't just a simulation. This is going to be a real thing that's going to live on a printed circuit board. So we're going to talk rather briefly about designing the circuit board and the two steps involved in that, and then I'll tell you a little about the hoops I had to jump through to test this thing and make sure it did everything it was supposed to do. Let's talk about doability. As with any project that might take up a lot of your time and attention and money, first thing you should ask is, has this been done before? Well, a POKEY's sort of been done before. People have written cores for it, and in fact, I was playing around with one when I built my Asteroids Deluxe in an FPGA. That had a POKEY core in it. But that was a POKEY core that was adapted to talking to a CPU that was also instantiated within the FPGA. That core was not suited for talking to an external bus or external hardware. So that was going to add a degree of complication. Also, no discredit to the guy who wrote it, it was a little bit glitchy. I mean, it was a wonderful creation, but I could tell that it wasn't quite right. And maybe that's just because I'm enough of a nerd who's spent a lot of time around these things and can hear the smallest difference between what it is and what it's supposed to be. However, it was great having a design that I could adapt to my purposes. I ended up using pretty much none of the original design. I rewrote everything from scratch, but having something to teach me, first of all, that this was possible, second of all, to give me some ideas about how everything worked, that was really useful. But despite the existence of all these Pokey cores out there in VHDL available for your downloading pleasure, nobody had built a working Pokey replacement chip. And this is the key question before you embark on any kind of engineering is, if this hasn't been done before, why not? Well, maybe nobody needed it. Well, I know that's not the case. Lots of people need Pokey chips. Lots of people collect these things, and their chips are always going bad, and they're paying ever-increasing prices to get more. So there is a demand. Has it been too expensive? Well, yeah, I think that's why nobody had done it before, because it was only in about 2016 that FPGAs became small enough and cheap enough that you could even consider putting one into a product that was only going to retail for about 40 bucks. Was it too difficult? Maybe some projects are, but this one probably is not. So the result of this analysis, yeah, it was probably too expensive in the past. So why am I the guy who should take this on? Well, I personally need them. I would love to have a big box of these for my own use, and that provides a lot of motivation to get things done when this is not just an intellectual exercise. If you don't build these yourself, you're going to have to pay somebody else a lot of money to sell you another one that may only last a couple of years. Besides, old parts may be cheaper now, and we may now have new parts that enable easier solutions. And as I alluded to a minute ago, that is certainly the case. What parts are we going to need? Well, obviously, we're going to need an FPGA. We're going to need a board to put the FPGA on. We're going to need some kind of memory to hold the configuration data for our FPGA. Some FPGAs have this memory built in, which is a very nice feature to have. But the ones that we're going to be using do not, and they're going to have to bootload themselves when you power them on and take their configuration data from a non-volatile memory that you've stuck onto the board. We'll need some glue logic. It would be great if you could just take the FPGA and wire its inputs and outputs directly to the external circuit, but that's not likely to work. You're probably going to need some kinds of buffers and drivers to sit in between your FPGA and the motherboard and direct traffic. We'll need a voltage regulator. The board you see sitting there, that's a 5-volt system. So it sends the original Pokey chip 5 volts DC. Well, our FPGA, being a modern device, runs on 3.3 volts. So we're going to have a regulator to convert the 5 volts to 3.3 volts and supply us nice, clean power. And last but not least, we're going to need a connector, have a set of legs that we can plug into the IC socket on that board over there. Let's talk about our performance specs, part of our design parameters. I wanted this thing to be universally compatible. The core that was written for Asteroids Deluxe, I did some experimenting with it, and it worked great for Asteroids Deluxe, but it certainly was pretty far from universally compatible. It sounded funny when you used it for any other game. And to make this a commercially viable product, I knew it was going to have to work in every arcade game that used a Pokey, and there's at least 24 of them. A lot of those games have more than one Pokey in them. Some of them have 4. So another design criterion was plan for multi-Pokey games. If you have one original Pokey and one of my replacements, they've got to be able to work together. If they don't, that's not going to be very useful. Sound, of course, has to be perfect, and part of that is it is going to require some attention to make sure that the volume output by the replacement chip has the same profile as the original Pokey. That is, outputs the same audio level under every circumstance. And the Pokey has kind of a funny profile. It's sort of a non-linear thing where, you know, volume 2 may be twice as loud as volume 1, but volume 20 is not twice as loud as volume 10. It's it's about 1.5 times as loud, if you can picture that. Lastly, these games perform all kinds of self-tests and diagnostics on the Pokey chip, and as far as the motherboard's concerned, I want it to think it's talking to the real article. So it's got to pass the self-test, and Tempest, in fact, goes a step further and tries to determine whether the Pokey is an original Pokey and not a counterfeit. Don't know why they would think anybody would ever counterfeit their chip, but that was a real concern back in 1980, is that you wanted your game to make money. You didn't want anybody bootlegging you before your game became obsolete. So designers often put some little tricks in there to discourage the would-be bootleggers, and Tempest has one. So we got to get past the anti-piracy check. Let's talk about practical constraints as opposed to performance. Number one being economic considerations. As I mentioned, you've got to be comparable to an original Pokey. You've got to leave some room for a little bit of profit margin. And the PCBs, the printed circuit boards we're making, I want them to qualify for these wonderful $5 specials that all these PCB makers are offering now, whereby they will send you anywhere between 3 and 10 absolutely perfect boards for $5. And if it's being sent from China, you'll have to pay DHL about $25 to ship them to you. But still, that's $30. That's a hell of a deal. I want that deal. So if the boards we're making don't qualify for the $5 special, they're wrong. Remake them. It's got to be small. Like I said, it's got to be no bigger than the original chip. Don't make it with parts that are obsolete or otherwise hard to lay your hands on. Mouser and DigiKey do not carry everything that you might want to use, so pay attention to that. And finally, manufacturability. There's no point building your design around a part that exceeds your ability to build into the board. And this is part of a philosophy called design for manufacture, which is a fancy way of saying when you're building it, make sure somebody can build it. It may look great in your CAD program, but there's a long way to go between there and having an actual physical product in your hand. And besides, when you're making prototypes, the person manufacturing it is probably going to be you. Let's talk a little bit more about DFM. There's a couple parts to that. The features on your printed circuit board, they've got to be etchable. They can't be so small that they all run together and create opens and shorts where you don't want them. And it must be assemblable, both in small quantities by your hands and in large quantities by robotic hands. That is a pick-and-place machine. And then once the parts are placed on the board, it's going to go on a conveyor belt and get sent through a pizza oven to melt all the solder paste, and bad things can happen there. When bad things happen, you get fallout. That fallout is what prevents your manufacturing yield from being 100% every time. You'll have parts that just didn't make it. On one of the cards that's being passed around, you'll see that one of my circuit boards didn't make it. It's got an error on it. And unfortunately, the manufacturer saw it and put that one in the scrap bin. About the etching constraints, we're talking about a constraint called trace space in PCB lingo. Traces being the width of a trace and space being the width of the space between traces. Now, if you are a manufacturer, what would you rather manufacture? A board that had big fat traces like this with lots of real estate on either side of it? Or would you rather have a customer that says, gee, to cram everything on my board, I had to use 4x4 trace space. You can make that, can't you? And increasingly, the answer is yes, we can make it, but it's going to cost you. So we have to find the sweet spot between component density and manufacturability. Let's talk about pad pitch. Pads being, the copper spots on your board that things actually get soldered to. Would you rather solder this component or this component? I know which one I'd rather solder, and it's the one with big fat pads with great big spaces in between them, because when they get too close together, you get solder bridges between them, and parts will fall out. Last but not least, let's talk about the package. So many packages these days, particularly for FPGAs, come in packages that are not friendly to hobbyists. What do I mean by not friendly? I mean they have no legs. Any package with legs, whether it's surface mount or through hole, I don't care, it's easy to solder. It's child's play. Once you get into the realm where the legs disappear to save space and the only connections to the chip are on the underside of the package, you can't cram a soldering iron under there. It becomes very tricky to do it by hand. You have to use hot air, you have to use a toaster oven, you have to have all kinds of tricks. In fact, any good board house, if they're putting a ball grid array package onto a footprint like that, to check their work, they will X-ray it after they're done with it to make sure that every ball and every pad have a good solder joint in between them. That's a lot of work, and that's one reason to stay the heck away from ball grid arrays when we are talking about hobby stuff. QFNs, quad flat pack no leads, you can do those. They're doable. They're hard, but they're doable. So let's pick some parts, figure out where we're going to get this stuff. What are our specs for the board? It's got to be cheap, it's got to be relatively thin, and we want it in a color we like. Well, let's just, jump ahead and say PCBWay.com, I think, is probably the cheapest manufacturer in the entire world. I priced out a lot of them. They are in Hangzhou, China, mainland China, and they do a real good job. I have ordered a lot of stuff from them, and they owe me a lot of free swag with all the points that I've now built up. And they let you pick any number of options. I picked 1.2 millimeters thickness. I picked 6.6 trace space because that's as small as you can go and still get the $5 special. Wants to know how big your drill holes are. The bigger the better, because small drill holes, there's more fallout. And here's the fun part. You get to pick any of these colors. I have done them all at this point, except matte black and matte green, because they're more expensive. What do we pick for our FPGA? The heart of our system. Because if we make a bad decision here, we're really going to be unhappy. It's got to be cheap and small, of course. We need enough logic elements that we can cram our whole design in there. And one of the big constraints, of course, is, as I mentioned, the number of I/Os that are available to us. Now, I counted up the I/Os that go into a real Pokey chip, and I got 24. 8 data bits, 8 bits for the potentiometer bus, 4 bits for the address, and 4 control signals. Finally, we want to use a 2-layer board with 6.6 trace space, because that's what we can get for $5 plus shipping. So let's open up the parts catalog and see what our options are. This is one of my favorites. The logo got a little garbled there, but this is the Altera Max 10. I love this chip. It's big, so it's easy to solder. It's got lots of I/O. It's got plenty of room inside. And although it is relatively cheap, it's not cheap enough for this project. It's about $6 each in quantity, and that's really too much. And it's also too big, which was a bummer. What about this one? This is cheap. It's small enough, satisfies all our other constraints, but it's a ball grid array. What does that mean? It means that we can't route it on a 2-layer board with 6.6 trace space. Well, why is that? The reason is, with a ball grid array, you have to do what's called breaking out the balls in the inner rows. And the only way to do that is either put a hole in between them and route the wire, the copper, through that hole, or more commonly, you'll try to squeeze a wire between these balls. And that can be done, but it requires considerably tighter constraints than 6.6 trace space. So that's out. This one gets the trophy. Why? Well, it's a quad flat pack no lead, 48 pins, and it gives us just enough user I/O for our purposes. It is cheap, it is small, it is wonderful. So I became a customer of Lattice Semiconductor. I love this chip. Incidentally, A very similar Lattice FPGA got put into the iPhone 7. And nobody's really sure why. Nobody knows what it's for. Everybody just knows that it's there. And in fact, this very same iPhone 7 board is glued to a piece of foam core that's been passed around because I had an iPhone 7 and it died on me. So I turned it into a prop. But that chip right there, that is a Lattice ICE5 LP4K, which is, although a different package and it's got more logic cells, it's essentially the same thing that I've put into my PokeyONE there. And of all the chips that you can choose from, it's kind of funny that I thought to be so closely related to what amounts to being essentially a famous FPGA. Getting tired yet? This part's about the configuration memory. Check this out. This is the one I wanted to use. It's that tiny. One of them is attached to the foam core board that I was passing around, and I actually had to put a red circle around it because when I showed it to people, they couldn't tell it wasn't just a spot of ink. This is the Macronix MX25 R512F. This is 4 megabits, so it's 512K fits into that tiny, tiny, tiny little thing. We're talking about literally the size of a head of a pin. And I thought that was so cool. And they are cheap, but there's some problems with them. Number one, Macronix's distributor network is not what I would call robust. I can't order them from Mouser or DigiKey just by going to a website. I actually had to call their distributor down in Huntsville and beg them to send me some, because if I designed it into my product, I'd be ordering millions of them every year. So you should send me some free ones. And they did. But a chip this small, being a ball grid array, you can imagine the kind of constraints that you'd need to break out this pin in the middle. I mean, forget about it. It's a DFM nightmare. So that's out. I ended up going with something not very sexy, but very easy to work with. It's a great big fat surface mount chip with 8 big shiny legs on it. They cost about $1/4 a piece. I don't love it, but it does work and it does fit. And the nice thing is you can root traces under it. There's nothing under there that blocks you from running wires underneath it. Glue logic. Why do we need glue logic? Well, like I mentioned, the Atari motherboard is a 5-volt logic system. Logic high is 5 volts. Logic low, of course, is 0 volts. An FPGA, on the other hand, a new one, typically runs at 3.3 volts for high. Well, what happens if you plug a 5-volt data line into an FPGA pin that's rated at only 3.3 volts? The answer is you fry it. It becomes permanently non-functional. And I actually have a fairly expensive FPGA dev board on which I have marked with a little dab of white paint all of the pins that I've fried by carelessly attaching 5-volt logic to them. So we're going to need something that sits in between our 5-volt system, the Atari board, and our 3.3-volt system, which is our FPGA. And it's going to take the form of some kind of buffer that doesn't do anything to the signal at all except translate its voltage level. Well, luckily Texas Instruments makes something exactly like this. Here's what's inside the chip. You got 8 parallel circuits here for 8 lines of data. Each one has a buffer going one way and another buffer going the other way. And at any given time, you can choose which side is the inputs and which side is the outputs. Very nice. And you could even get in a big fat dip chip with legs, but we don't want that. We want the little one. Why do we want the little one? Little ones cause problems. Well, the problem is for this design, we need 3 of them. And to cram 3 of these chips onto that little board, the chips are going to have to be as small as we can get them. I'm not going to talk much about the voltage regulator, just to say that the part that works is this nifty little thing that gives us all the voltages we need with lots of power, and it's the size of a grain of rice. It's amazing. It's cheap, but not super cheap. These are still about $1 a piece. So don't drop them on the floor, because you'll never find them again. And the connector. What are we going to do about the connector? Well, originally I was going to use these things. You know, they're super cheap. They work really well. But I wanted to make my chip short, height-wise, and these things have pins that stick up through the top of the board, and that's how you solder them on there. And I didn't want to have to go through, hundreds of boards and take a Dremel tool and grind them down flat. So, they had that drawback. Also, this is a through-hole component. All the other components we're going to be using on our board are surface mount components. And there's nothing to say you can't mix surface mount components with through-hole components, that go through holes on the board. But if you're going to have these things assembled professionally, they charge you a lot more if you have mixed technologies. So if possible, you really want to stick with something that's surface mount. Wow, here's something that's great. Here's a surface mount connector, and these little pins, they have sort of an L-shaped curve in them, and they'll sit flat on your pads, and they'll get soldered down by the robots, and everything will be great. Thank you, Presidip, for this wonderful product. But wait, you want how much for it? This thing costs $6. And if you buy 100 of them, you can get them for $5. That's a total non-starter in a product that we can't price any more than 40 bucks. If only we could find the equivalent thing, but much cheaper. Where would we find such a thing? Turns out there is a place in China that I found after much searching and much back and forth with their sales rep that is equivalent in every way to the $6 part, and it costs quite a lot less than $6. To maintain my competitive advantage, I'm not going to tell you where I got them or how much I paid for them. Let's just suffice it to say, when the president talks about how we're getting screwed on our trade relations with China, I have kind of mixed feelings about that. All right, we're through the death march of picking our parts. What have we learned? When you're planning your design, of course, write up a spec. Define what kind of performance you want. Then you can determine what parts will provide that performance for you. Then you got to choose what devices and in what packages are going to work for you. And of course, they got to meet your physical constraints, like size and all your design for manufacturer concerns. And they got to meet your cost constraints. And we walked through the part selection for the PokeyONE and the reasoning that I came up with for everything I chose. Having thought about this quite a lot since I made these decisions, I don't know how I could have done them any other way. I got incredibly lucky by being smart and figuring out what was going to work before I got too far down the wrong road. All right, what's next? Let's talk about how to program, again in quotes, an FPGA. As I said, you got your choice of two different hardware description languages. I'm going to talk about VHDL because I know it way better than Verilog, and I think it's a little easier to explain. Once again, not a program, it's a description of a circuit, and it looks like code, so I like to call it code. Like code, you go through what seems to be a compiler. It's called a synthesis tool in FPGA speak. So if you really want to be correct, don't talk about compiling your code, talk about synthesizing your code. And then finally, once we've gotten a design, we have to implement it. What do I mean by that? You've got to define, first and foremost, a pin out. You've got to tell your chip which pins on the actual physical chip are going to represent which signals. Then we're going to let our design software do the heavy lifting of placing and routing, that is, coming up with the magic way to define all these logic resources within the FPGA, something that is completely opaque to me. All I know is when it's done, you have a nice little binary file that you can burn into your device. So here's the block diagram for the PokeyONE. Outer layer, we got our PCB. On the PCB, we have our FPGA chip, our voltage regulator, our memory, some stuff to process audio. We've got the clock coming in from the motherboard at about 2 megahertz. That's important. And we've got these level shifters so that we don't fry the inputs on our FPGA. Inside our FPGA, we have a couple of VHD modules, which are the code that we've written in VHDL. And you can see that certain modules are instantiated within other modules. In any VHDL or Verilog design of any complexity, you're always going to have a file called top, which of course is the top level instantiation and tells you, what the next level down is. What's inside the Pokey? Well, we've got 16 memory registers that we can store 8-bit numbers in. We've got a random number generator. We've got logic for sending data in and out. We've got clock dividers. The Lattice FPGA has a built-in oscillator, which is nice. Saves us about $1, which goes all the way up to 48 megahertz. That's a great thing to have, because by dividing it, you can get any clock you like. We've got some logic for reading the paddles. And lastly, we've got the sound generator. And that's basically the whole enchilada. Let's talk about the code itself. And I've written a short example here. This is not a dumbed down example. This is real VHDL code. This code will synthesize and do what I'm about to describe for you. So, you would never use an FPGA for this simple purpose, but you could, and this is how you would do it. What's our circuit here? Let's have a push button and an LED. And the performance characteristics are every time we push the button, if the LED is on, it turns off, and if it's off, it turns on. So how do we implement this in an FPGA? Well, first you declare an entity. What's an entity? Well, it's the thing that's being made by that module. This one has one input and one output. The input is called switch. The output's called LED, and entity. That's it. That's all we need to define. We then define what's called the architecture, how this thing is supposed to work. We're going to define an internal wire that's not shown here, but you can imagine it running somewhere inside this FPGA. We're going to call it LED state. It's standard logic type, which means it's either a 1 or a 0. That's it. Begin. What is this thing going to do when you switch it on? Well, the port called LED is going to be whatever the wire LED state is. It's going to be a 0 or a 1. Here's the interesting part. This is what determines what happens when the state of switch changes. Whenever switch changes, it will trigger this process and do this, which is what? Well, it checks to see if the current state of switch is 0. Have we grounded this pin by pushing the push button and shorting it to ground? If we have, then we're going to do something. Namely, take our LED state and turn it into the inverse of whatever it was already. So 1 becomes 0, 0 becomes 1. End if, end process, end architecture. That's it. That's the whole thing. And that is a real VHDL program. I hate calling it a program. It's not a program, but it's code. So once you write code for all of these modules, what you end up with is a collection of VHD files, which I have found can very easily be managed with Git and stored in GitHub or Bitbucket. This is a screenshot of my PokeyONE VHDL repository, and it's got these files in it, some of which got updated a lot, some of which got finished months ago and never touched again. Let me talk a little bit about the digital analog converter in my chip. I'm kind of proud of it because if you needed an outboard digital analog converter, boy, they're expensive, they take up a lot of room, and they introduce a lot of room for error. So I built the DAC right into the FPGA through a technique called pulse width modulation, which I won't get into, although you can certainly talk for hours about its nuances. You can generate an analog waveform by outputting 1s and 0s fast enough and then sort of using a capacitor resistor network to filter the results, and you end up with a nice wavy curve instead of a bunch of 1s and 0s. But to do this, my VHDL module for the DAC, it has a volume table which says that whatever volume comes in, 0 to 60, correlate that to a PWM duty cycle, which is 0 to 127. And like I said, it's not linear, it follows a pattern. I had to determine that pattern by experiment. I actually had to build some breadboards and feed it a volume and look at my scope and see what the analog output was and write it down on a piece of paper, which I then coded into a table in PokeyDAC.VHD. All right, got to catch my breath. We're at a summary slide again. We, as the designers, we are able to define a physical circuit in an FPGA by doing nothing more than writing a description of it in Verilog or VHDL. And we know that that is not a program, although it looks like one. All of our modules are going to be instantiated within top.vhd, or if you're using Verilog, it'll be top.v. We should draw ourselves a block diagram to help us visualize how all these modules and submodules are going to be instantiated within each other. Next, I'm going to take you on a very quick spin through electronic design automation. And again, EDA is, for making circuit boards, is a very broad topic, and I could spend 90 minutes talking about that real easily, but I'm not going to. We're just going to hit the main points. There's two parts to EDA, schematic capture and board layout. And very often, the software that does these two things will be two discrete, separate programs. I like to use Eagle. That's my jam. You might be a KiCad person, or you even might be a Fritzing person. But Eagle is the one that I've worked with for the last 10 years, and I've gotten used to everything that's wrong with it. And since Autodesk bought it, they've actually made it quite a lot better. So the examples you're going to see were all generated by Autodesk Eagle. Here's schematic capture. I don't know why they call it capture. You're not capturing anything. You're drawing things. What are you drawing? After you have defined a device you want to use in your parts library, with any luck, somebody else has already designed it for you, and you can just click Add and drop it onto your screen, and there it is. So you add all your devices, and then you draw nets. Nets are these little green nubs that represent your connections. And the way I like to do it is you just draw a little stub on every pin and give it a name. Here's P6L on the FPGA, and well, bad example. Imagine D7L and D7H were the same thing. One's actually a level shifted version of the other. I mean, I could just draw a line from there to there and define that connection. But an easier way, and it keeps your schematics cleaner, is if you just put a stub on it and give it a certain name, your program will know that everything with that same name gets connected together. Here's a slightly more readable blow-up of the Pokey that I defined. And it's got all the same pins as a real Pokey, of course. After you're done with schematic capture, you go to PCB layout. Well, we have a two-layer board, so we've got two colors. Red is the stuff on the top layer, and blue is the stuff on the bottom layer. You can see this is where we'll attach our FPGA. These blue things are the pads on the bottom side of the board where our fancy little L-legged connector is going to get tacked on. But what are all these yellow lines? Well, that's where the rubber meets the road in PCB layout. Those are called air wires. Air wires represent connections that need to be made between one pin and another pin. And you, as the designer, have to figure out how you're going to make those connections. That can be really tricky. There are two ways to do it. You can do it by hand, or you can use an auto router program that does the best it can to figure out how to connect everything together and leave nothing unconnected. The dirty secret of auto routers is they're not very good. When your circuit reaches any level of complexity, your auto router is going to hurt you more than it helps you, although it sometimes helps you get started. So, here's the PCB for my PokeyONE. Everything you see here was routed by hand. I turned each and every one of those yellow air wires into a real trace just by figuring out how to do it. The only other thing I wanted to mention here is these little green dots. Those are called vias. Vias are drill holes in your PCB that are plated through with copper so that they connect a trace on the top side of the board, like this long red one, to a trace on the bottom side of the board, like this blue pad. So that allows you to have a two-side board in which the top and the bottom can be connected to each other. This comes in handy when you have to route traces from one place to another and you can't have traces crossing each other on the same layer. So you drop some vias and route one of them through another layer, and they pass over each other. I could spend hours, and in fact have spent hours, dragging traces around, trying to make it as neat and tidy and artistic as possible. It's a weird obsession I have. Here's the end product. You can see that the physical reality looks pretty much like it looked on the computer. The buffers, there's one, there's two, they end up as these things. Here's the FPGA, it gets soldered down just like that. Here's another buffer. Here's our flash memory. You can see how we routed a whole bunch of traces in between the two rows of legs, and that package let us do that. And here's our dinky little voltage regulator. And that's it. That's everything we had to do to lay out the PCB. I wish I could have made it bigger. Everything would have been a lot easier, but as it was, I had to use fine pitch pads, things that were real close together, with no legs. That means it's hard to assemble, either by you or by a robot. And like I said, layout is challenging. You have to put a lot of thought into where you're going to put each and every component, because if you don't put them in exactly the right place, it may not actually be possible at all to route all your connections in the number of layers you've defined. And of course, a small board has tight routing. You know, that's about as tight as 6.6 routing can get. You know, if there's not much room to get creative when you know that all your pins are that close together. But there is one huge advantage of having a small PCB, and that's that PCB manufacturers often charge you by the square inch. And if your board is small, then it's very cheap. PCBWay in Hangzhou, they would send me 10 of these things in 6 days. 6 days! It wouldn't even take a week to get them all the way across the globe for 30 bucks. Oshpark, which is domestic, they take a little longer, but they charge you half as much. And they only give you 3 boards, but you know, if you're prototyping, come on, how many do you need? But when you have cheap prototypes, that means you go through a lot of prototypes, which I did. Oh, we're going to have to start that one again because y'all made me turn off my volume. This part has volume. No, not that. Sorry, guys. Help! This was going to be the best part, too, I swear. Come back. Yeah, y'all just talk amongst yourselves for a minute. Oh, here we go. I work on computers for a living, can't you tell? All right, we're back on track now. What was I saying? Yeah, there's a rule in engineering. Don't make a lot of prototypes. Make as few prototypes as you can. But when you can have a new prototype in less than a week and it barely costs you anything, you know, why not make a lot of them? So I did. It's a little embarrassing that I went through this many prototypes, but I forgive myself for 2 reasons. It didn't cost very much, and we ended up with a working product, so I can still sleep at night. Around version 8 of that big series of boards that you just saw, I got stuck, and I mean really stuck. Sounds weren't right. I mean, they're mostly right, but that's not good enough. You put a Pokey prototype in these boards, and some of them wouldn't boot, and some of them would. And Tempest kept crashing on me, and because it's got that anti-piracy protection, I knew that my random number generator wasn't working the way it was supposed to. But fate intervened. I was introduced by a mutual friend to this guy, who is a professor of physics and engineering, and in fact the head of the department down the road here at Trevecca Nazarene. Fred Cawthorn is a video arcade game collector, even more specifically of Atari video arcade games, and he knows more about FPGAs than I ever will. I managed to get him interested in this project, and that was a very lucky thing because he solved a lot of problems. We had some bus contention issues. If you know anything about buses, you can't have two devices talking on the bus at the same time because they'll try to talk over each other and nobody will get understood. He figured out how to fix that. He fixed my noise mixers. He fixed my random number generator. He spent, I can't even tell you how much time calibrating the DAC with tools that he built in his basement specifically for this purpose. And he identified problems I didn't even know I had. Turns out that Atari in these games was not consistent in the topology of the audio amps that they used. They used two different types, but even then they weren't all the same. And we had to account for that because our DAC would sound different depending on which topology it was plugged into. So he had the bright idea of having our chip have two discrete audio outputs, both of which go to the audio out pin, but when the chip starts up, it does a little test of its environment and figures out which one of its outputs it's going to use. I thought that was brilliant. It's even more brilliant because it works. The other thing he discovered was something I never would have guessed at, and that is that all transistors are not created equal, and our DAC, which relies on an external FET, a field effect transistor, for switching, the sound ends up being dependent on the characteristics of maybe individual FETs, but certainly different brands of FETs. What do I mean? Let me show you some scope traces. Here's a good FET from a name brand supplier, good old ON Semi. When we use that, our gate turns fully on, goes boing, is immediately high and then immediately low again. The drain, which starts at high, goes immediately low and stays that way and has a little bit of a tail on it, but not much. It ends up sounding great. I had a run made in China, and I told them, use whatever BSS 138 transistors you've got in the factory. Probably doesn't matter. So they hooked me up with the fine products of the Titron company. Well, compare that trace to that trace. And you can see that this one really isn't doing what it's supposed to be doing. Not only does the high not go low and the low does not go high, but this thing doesn't even start to move until like one whole time division after this one goes high. You can hear the difference immediately. This thing sounds all distorted and weak and crappy. And it only took a day or two before Fred said, "Are you sure it's not the FET?" I said, "Well, how could it be the FET? They're all the same." He's like, "Well, are you sure?" Yeah, he put his finger right on that one. That's a duplicate slide. Talking about some testing here. There's a problem with testing something like the PokeyONE. There were a lot of instances where we thought we had it working great, but every new game we tested, we'd find a new bug. Working in one game did not guarantee it was working in all games, and you could very easily convince yourself it was working 100% because you hadn't yet tested what wasn't working. You wouldn't even necessarily know that. Like the random number generator. Centipede doesn't care at all whether your random number generator is, works completely differently than the original Pokey. It'll run just fine. Tempest, on the other hand, will complain vociferously and not run for you at all. Also, with the sound output, we calibrated the DAC like for the Tempest audio amp configuration. And then when we put the same configuration into Star Wars, it wouldn't work. Why? Star Wars has this other amp configuration, and we wouldn't have known there was anything wrong unless we tested it. I mentioned the bus interface logic, the contention issue. Again, it worked in some games, And if we didn't keep testing exhaustively, we might have just thought it would work in everything, when in fact it wasn't going to. This was a real pain, especially when we were testing on games that neither Fred nor I had in our personal collection. In those cases, to test a new spin, you were going to have to jump in the car and go drive to somebody's house who had one of these things. Or a couple of times I actually had to put them in the mail. Fortunately, we as Nashvillians have the benefit of the Game Galaxy Arcade down in Smyrna. I don't know if any of you have ever been there.
My son was there.
It is nirvana.
I poked my head in once and it was just overwhelming.
It's almost overwhelming. Jason Wilson, the proprietor of Game Galaxy, has created one of the best classic arcades in the country just down the I-24 in Smyrna. Jason also has what many people suspect is the largest personal collection of console cartridges in the world. He has, I think, 50,000 of them. But he is very generous with his colleagues in the collecting community, and he invited me to come down and do final testing of this chip on his machines. And in one day I knocked out about 10 or 11 different machines that I could confirm now worked. One of them was kind of special, and that is Warlords. Warlords is the only one of Atari's 24 Pokey games that actually uses the paddle scanning circuitry for analog scanning. And I didn't have that code written. I didn't think I was ever going to write it. I thought, you know, it's just for one game. It's a really rare game. Heck, Jason has the only one in all of Middle Tennessee, as far as I know. Nobody's going to miss it. But we didn't want to say this works in everything except this one game. So I wrote up some code as best I could, and I took it down to Smyrna, which is a long way from where I live in Fairview. So I was only going to get one crack at this, and I plugged the board in, and lo and behold, it worked. And all the little doodads moved around just the way they were supposed to. It was like a moon landing, you know? You weren't sure it was going to work until it worked. So this turns out to be a really fun game, by the way. What am I going to do in the near future? Well, I am planning on a version 2 because all the people in Atari age who have 5200s and 7800s and they have home computers, they're all kind of pissed off at me because my chip doesn't work in their machines. So I'm going to have to fix that. It involves a couple of things. I'm going to have to change the size and make it even smaller than it already is because the 7800 takes a Pokey and actually crams it inside one of those Atari-sized cartridges. That's going to be tough. But I'm also going to have to implement the features that I left out of version 1, which is, you know, the arcade-only version. What things are those? Well, serial input-output for modems and printers and disk drives. Keyboard support. It's got to support the keyboard. A real Pokey has an IRQ line, so I've got to wire up some code for that. But I got a problem, which is that on my current design, I'm all out of IOs. I've used them all. Yeah, so what do I do now? Well, you know, when in doubt, add more IOs. Lattice makes this chip. This is the mutant sibling of the chip that I've used in version 1. It has all the 48 pins on the outside, but then it has 36 more pins on the inside. Gives you 67 IOs, which is way more than I need. And it doesn't even really cost anymore, which is great. There's a problem, though. And it's sort of the ball grid array problem as applied to a 2-row QFN. Well, I might have to go to 4 layers just because I'm adding more traces. But the real problem with using this QN84 package is it needs 4-4 trace space, and here's why. Here's an Eagle screen capture of a board I laid out just for practice with this package. Here's the inner layer. Well, you got to break out these inner row pins by putting them in between the outer layer pins. Here's a 6mm trace. This is the one you get with your $5 special, and that's what the current version 1 is made with. Yeah, I'm not going to be able to use the $5 special anymore. And that's a real problem because, to get 4 trace space, I'm going to have to order PCBs that cost about 10 times as much. Ouch.
For another year or so.
From your lips to God's ears. All right, we have reached the end. What have we learned? We got these things, FPGAs. They're ASICs that you can reconfigure, and that's a glorious thing. You can use a modern FPGA to clone a really old ASIC that may be failing on you for reasons unknown, but probably related to it being 40 years old. The only way I was able to make this PokeyONE, there's a few factors that went into this. Small, cheap FPGAs. Couldn't have done this before Lattice released those things only 3 years ago. The design software, both from Autodesk and from Lattice, is free. Now, Autodesk will charge you if you want to do bigger boards, but these boards are so small, they actually were compatible with the free version of Eagle. That was huge. Can't underestimate how important this third one is. Inexpensive boards and assembly that I can afford. I priced out some domestic manufacturers of printed circuit boards who also offer assembly services. And it wasn't going to be a little more expensive to build these things within the United States. It was going to be anywhere between 6 and 10 times more expensive. Wow. So, you know, I have to thank my new friends and partners in China because they did me a solid. You know, without their service, these things wouldn't exist. Finally, I have to thank everybody out there who's actually interested in buying one of these things because I got to order, you know, a sizable quantity of them. And of course, the more you order, the cheaper you can make them. If there's any moral to this 18-month voyage, it's that, you know, you can really amaze yourself at what you can do if you have enough time, money, and help. Here are the people who have helped me. This is Fred, of course. This is Chris Royalty, one of my best friends. He runs Hot Rod Arcade, which is the web-based business that sells these things. He is also a collector and dealer of video games and pinball machines, probably one of the biggest in the state. This is the aforementioned Jason Wilson, proprietor of Game Galaxy, a local celebrity that should be better known. And last but not least is my friend Jason Kopp, who runs the YouTube channel Arcade Jason. I was up in Ohio visiting him about 6 weeks ago, and we made a video about my PokeyONE chip that has turned into sort of the promotional video for this chip. And it's turned out to be very popular, and it's really helped us with the launch of this thing. It was great to get out of the gate with that kind of publicity. I am David Shuman. I really thank you for your time. I will leave this slide up because if you want to get an FPGA dev board, this is my suggestion. Thank you all very much.